Alright, gang, here we go. This is for Chem 2, Unit 13, talking about concentration cells and doing some practice with voltaic cell and Nernst equation calculations. Alright, so concentration cells, to start off, remember last video we talked about the Nernst equation. We talked about how we can calculate the electrical potential of a cell at non-standard conditions using this equation. So we have first we start with the electric potential of the cell at standard conditions, and then we subtract the RT over NF, right? And NF. F is Faraday's constant, R is 8.314, temperature is in Kelvin, and then our N value is the number of electrons that are transferred per half reaction times the log of our Q. And remember, that's our reaction quotient. All right, so essentially what we can do, what this teaches us here, is that we can actually have, if we choose our concentrations correctly, we can have a electrical potential that gets generated purely by having a difference in concentration. Because if that log of that Q gives us a new concentration or some non-zero answer, then we'll have an electrical potential. And if we can make this whole thing equal a negative number, we can actually have a positive potential. So in this example here, they've got nickel. All right, and they've got this this nickel concentration cell where they start at a really small concentration of nickel on one side and then a very large concentration of nickel on another side. And so the electrons travel from one nickel anode to the nickel cathode. All right, and it's all because of this concentration difference from 0.001 molar to the 1 molar solution. And we can see as it gets discharged, we have a 0.09 potential difference. And then on the other side, once everything's equal and these concentrations are equal to one another, we have zero voltage. Okay, so we can have this voltaic cell occurring even without having two different substances. Now, really what they're trying to do is reach equilibrium, so those concentrations will be equal to each other. All right, and so we can have, essentially this bullet point is exactly what we just explained. The Nernst equation implies that a cell could be created that has the same substances as both, and that's known as a concentration cell. All right, and so as long as those concentrations are different, the E will not equal zero. All right, so that's about it for concentration cells. So now let's do some practice problems here. So this first one, we're going to calculate the concentrations in a voltaic cell. All right, so we're going to have a conductivity probe is essentially what this means, is we'll be able to measure the potential difference between two cells and then be able to calculate the concentration. So here they said if the potential difference of a zinc hydrogen cell is 0.45 volts at 25 degrees Celsius, and the zinc is equal to 1 molar, and the partial pressure of the hydrogen is equal to 1 atmosphere, what is the pH of the cathode solution? So we're going to walk through this one and then we'll try one on our own. All right, and so they got a little diagram set up. I almost always encourage you to go ahead and write this out. Write out what you know, okay? And so it's got zinc here, and then hydrogen here, and then we know that the zinc is the anode, and then the hydrogen would have to be the cathode. And we know that because of the potential difference of the zinc to the hydrogen. All right. So anyway, so zinc gets oxidized and the hydrogen gets reduced. And so we can draw where the ions are going. Remember, the anions go towards the cathode side, or the anode side, and the cations go towards the cathode side. All right. So there you go. All right. So essentially, all we have to do is, if we know that the pH of a solution is equal to the negative log. Right, the pH is equal to the negative log of the concentration of H plus. So if we can figure out what the concentration of the H plus is over here, then we can figure out what the pH is. Okay, and then we could figure out the concentration of the H plus by using the Nernst equation, because we know that the Q value in that Nernst equation has the H plus inside of it. So if we can find the Q and we have these other concentrations already, we have the atmospheric pressure, or the partial pressure of the hydrogen, we also have the concentration of the zinc, then it'd be simple enough just to rearrange it to solve for the concentration of hydrogen. All right, so let's walk through what they do here with them. Okay, keep going so we get all of the little bits and bobs here. All right, and it says the cell reaction is this. All right, so they've taken your two half reactions and written the overall equation. All right, and so the first step is you got to find your E cell, all right, standard. So you go reduction minus oxidation, and we know that the hydrogen is on the cathode side, so that's where the reduction occurs, and hydrogen cell is 0, right? We've defined it as 0. And then the zinc cell is oxidation, right? So it's on the anode side, so we add the 0.76, and so our our E cell standard is 0.76 volts. All right. We also know that the N value equals 2. Okay, because we're going to be, we have this change from 0 to positive 2. So we're losing or gaining 2 electrons per half reaction. So our N equals 2. All right, they give us the 0.45. This is the Nernst equation right here, right? E equals E standard minus, and this is all this R, T, and F all put together. So 0.0592 R, T over N, F log Q, right? So they're just plugging in their values here. 0.0592 divided by 2 times their log Q, and they rearrange to solve for the log of Q. And they get 3 times 10 to the 10th. Now, based on this equation here, we know that the Q value is going to be equal, remember, it's the products over the reactants, all right? And we don't include solids or liquids, right? So it would be the concentration of the zinc times the partial pressure of the H2 over the partial pressure, or the concentration of the H plus, but the H plus needs to be squared because we've got the 2 right there. All right, and then essentially we know from before the zinc is concentration of 1, the partial pressure of hydrogen is 1. We can rearrange this to solve for hydrogen, right? So here they've said, essentially what they're doing is just rearranging. So they find eventually that the concentration of hydrogen is equal to 6 times 10 to the minus 6th. All right, so that's the concentration. We can take the negative log of that, and that's the pH of your solution. And this is really how pH probes work. Like in a pH probe, essentially what you do is you've got like a little deuter right here, like a little pen-shaped thing, right? And you've got like a little glass bulb at the end. All right, and then this glass bulb is where our ions can travel between them, and we just set up 2 solutions inside of here. You usually have a standard solution, okay, that just stays inside the plastic or the glass coating or whatever your pH probe happens to be made out of, and then you stick the other end in your other solution, and it can measure the conductivity between these two, the current flow or the voltage difference between the two, and then from there the computer will automatically just essentially run through all these calculations. It already knows what the standards are, right? And then so really all it's doing is just solving for that unknown based off the voltage. All right, so let's try this one here together. All right, so this is using same idea, but we're doing the pH using a concentration cell instead of like a regular voltaic cell. All right, so it says a voltaic cell is constructed between 2 hydrogen electrodes, and it says electrode 1 has a partial pressure of hydrogen of 1 atmosphere and an unknown concentration of H+. So that's really what we're after. And then electrode 2 is a standard hydrogen electrode, and it's got 1 atmosphere and 1 molar. Okay, at 298 Kelvin, the measured cell potential is 0.211 volts, and the electric current is observed to flow from electrode 1 into electrode 2. All right, so let's see if we can kind of draw what's going on here, and even though these are gases, so on and so forth, we don't really have to be too particular about it. So we got our salt bridge, whatever, okay, and then we've got our electron flow is going to go from here to here. We'll put in our voltmeter because we're cool. All right, electrons go like this, okay, and they come back here, going this way, and this is 0.211 volts. All right. So down here it says we have a partial pressure of H2 is equal to 1.00 atmospheres, right? This is our electrode 1, or maybe we'll label that as 1, and this is 2. And it says the electrons flow from 1 to 2. That's why I made the electrons go from the left to the right. And then the concentration of the H plus is unknown. Okay, so we'll call that X molar. All right, and then on the other side, our partial pressure of our H2 is also equal to 1.00 atmospheres, and then the concentration of the H plus is known, and that's equal to 1.00 molar. Okay, all right, so that's where we're at so far. Okay, now so we can start off the same way as they did before. We're going to use the Nernst equation, right? So we know that 0.211 is equal to our E standard, right, minus our 0.0592 divided by the N times the log of our Q. All right, so we got to fill in a couple of these other spots. Now, since it's a standard, the standard cell, since it's a concentration cell and we have hydrogen go into hydrogen, we could write out these 2 half reactions. So at electrode 1, what we've got is it's being oxidized. So we're starting with H2, and it's getting reacted to make 2 H pluses plus 2 electrons, right? And then at electrode 2, it's the exact opposite, right? 2 electrons react to form, or plus 2 H pluses react to form our H2. All right, so that's kind of what we're sitting at. So our overall reaction, now you might be tempted to say, well, this completely cancels. Now, the trick here is that they only cancel if their concentrations are equal. Now, when we take these two reactions here, these two hydrogens, these are gaseous hydrogens, and they are the same pressure, so they will actually cancel when we write them in together. But the H pluses are at different concentrations. The electrons obviously cancel. So the two H pluses that are on the product side, or the reactant side, excuse me, are the known concentration. So we'll just go ahead and say this is 1.00 molar, right? Because this is on our electrode 2, which is the 1.00 molar. And then on the product side, you have two hydrogens, but they're at X molar. Okay, so some unknown molarity. All right, and so that's kind of where we're at now. Now, to do cathode minus anode, we know since they're both hydrogen cells, they're both defined as 0, so our E standard is going to be equal to 0. So this becomes 0.211 is equal to 0 minus 0.0592 divided by our N value. And then our N value was 2, because that's how many electrons are being transferred, and that's equal to log of Q. All right, so to solve for Q here, remember, we're going to take the 0 goes away, and we're just going to multiply by 2 divided by 0.0592, and then 10 to the whatever for that guy. All right, so our Q value, if we do all that, earlier I got my Q value was equal to 7.4 times 10 to the minus 8th. All right, so plug that in your calculator, see if you get the same thing. Hopefully you do. All right, so 7.4 times 10 to the minus 8th is our Q value, and now we know based on this equation here that our Q is equal to the concentration, or products over reactants, so it would be the concentration of H plus squared over the concentration of the reactants, which would be our 1.00, and that guy squared, right? And so this is going to be equal to x squared over 1, right? So if we do that math, so x is going to be equal to 2.7 times 10 to the minus 4th. So that's our concentration of H plus, molar H plus. All right, and then to find the pH, we just say pH is equal to the negative log of that guy there. So 2.7 times 10 to the minus 4th. All right, and I got 3.57 when I did that earlier today. All right, so that's how you calculate the pH using a concentration cell. It's not too terribly difficult, but there is a lot of pieces to keep in mind. Essentially, what you got to remember is that you're solving for that Q value, and remember which part of the Q value you're solving for. Separate it into cathode and anode, just take it one step at a time, and just try to remember, set your end goal, try to work the problem from both ends, then focus on one step at a time. All right, so anyway, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.